Section: Introduction. In this section, we explore how transformer-based large language models, LLMs, pre-trained on extensive text data can be used for feature selection in supervised learning tasks. By providing task-specific prompts to the LLMs, we can prompt them to identify the most relevant features for predicting outcomes in a downstream task. This process involves ranking features based on their importance or generating feature importance scores for each candidate feature. Surprisingly, we find that LLMs can effectively select predictive features without directly looking at the training data. Even without prior knowledge of the data distribution, these models can rival traditional data-driven feature selection methods like the LASSO. This result challenges the common belief that selecting features solely based on their names may not be effective due to variations in data distributions. Our experiments demonstrate that even zero-shot prompting, where no additional context about the data is provided, can lead to strong feature selection performance, especially with advanced models like GPT-4. We compare our LLM-based feature selection methods with traditional approaches on various real-world datasets and show that LLMs can perform competitively in selecting predictive features. We propose 3 approaches for using LLMs in feature selection: selecting features with high LLM-generated importance scores, ranking features based on LLM outputs, and sequentially selecting features through a dialogue with the LLM. Our findings indicate that larger language models tend to produce feature importance scores that correlate well with commonly used metrics like Shapley values. Overall, our study suggests that LLMs can not only help in selecting predictive features post-data collection but also aid in deciding which features to collect initially, particularly in fields like healthcare and social sciences where high-quality data acquisition is costly. Section Summary. In this section, we explore the capability of large language models, LLMs, to perform feature selection for supervised learning tasks without directly looking at the training data. By prompting the LLM with task-specific instructions and examples, we demonstrate that LLMs can effectively identify the most informative features for predicting outcomes, rivaling traditional data-driven methods like the LASSO. Our findings suggest that even zero-shot prompting with LLMs, such as GPT-4, can lead to strong feature selection performance, indicating the potential of LLMs in guiding feature selection and data collection decisions, particularly in domains like healthcare and social sciences where high-quality data is costly to obtain. Section: Chain of Thought Prompting, COT. In this section, we introduce Chain of Thought Prompting, COT, a method that enhances input-output examples with a series of natural language reasoning steps leading to the correct answer. When it comes to decoding, instead of using greedy decoding where the token with the highest probability is chosen at each step, we employ self-consistency decoding. This method involves sampling multiple outputs from the language model and combining them to make the final prediction. Self-consistency decoding is particularly useful for COT prompting as it can improve performance, especially when there are various ways to solve a task. Feature selection is a fundamental issue in machine learning, where the aim is to choose the most informative subset of features from a given set. There are 3 main categories of feature selection methods: filter, wrapper, and embedded methods. Filter methods rank features based on certain criteria and select the top ones independently of the learning algorithm. Wrapper methods search for an optimal feature subset that maximizes the model's performance. Embedded methods incorporate feature selection into the model learning process, often using regularization techniques to promote feature sparsity. In our experiments, we compare our methods with traditional feature selection approaches from all 3 categories. In a related work, the LM-Priors framework prompts a variant of GPT-3 to determine which features should be used for predicting an outcome based on differences in log probabilities. Our approach differs in that we propose 3 feature selection methods that directly utilize the generated text output rather than token probabilities, which are not always accessible in closed-source language models. Additionally, we conduct a more extensive evaluation across different model scales and prompting strategies on various datasets, providing practical insights. When it comes to selecting features using language models, we focus on supervised learning scenarios where our goal is to learn a prediction model from labeled data. We assume access to textual descriptions of input features and the prediction target. Our objective in feature selection is to identify a subset of features that leads to a high-performing model under a given budget constraint. To leverage a pre-trained language model for feature selection, we prompt the model with input and target concepts and select features based on the generated output. We consider three approaches: selecting features based on importance scores, selecting features based on a ranking, and sequentially selecting features through a dialogue with the language model. Each approach has its own prompt template tailored to the selection strategy. Section Summary. In this section, we introduce chain of thought prompting, COT, a method that enhances input-output examples with a coherent series of reasoning steps to improve accuracy. We also discuss self-consistency decoding, a technique that involves sampling multiple outputs from a language model to enhance performance, especially when diverse reasoning paths are possible. Additionally, we delve into feature selection methods in machine learning, categorizing them into filter, wrapper, and embedded methods, and compare our proposed methods against traditional baselines across various datasets and model scales. Section: Selection based on LLM-generated feature importance scores, LLM score. In this section, we base our selection on LLM-generated feature importance scores, LLM score. We ask the model for a set of numerical feature importance scores, where each score indicates how closely an input concept is related to the target concept. We then identify the top K concepts with the highest importance scores and use them for learning. The importance scores are derived directly from the text output and do not relate to token probabilities. We also test the sensitivity of LLM score to different score ranges. Another method we explore is based on an LLM-generated feature ranking, LLM rank. Here, we request a ranking of all input concepts based on their relevance to the target concept. We select the top K highest ranked concepts for learning, assuming that the rank reflects the importance of each concept for prediction. In the LLM-SEQ approach, we adopt a sequential selection strategy where we iteratively add concepts to maximize cross-validation performance. We start with an empty set and gradually include concepts that improve performance until we reach K concepts. We hypothesize that this method encourages selecting informative features that complement the already chosen ones. For our experiments, we utilize LLMs like GPT-4, GPT 3.5, and various llama models with different parameter sizes. We do not fine-tune the LLMs on the downstream dataset to maintain fairness. In terms of prompt design, we present various templates that have shown effectiveness. We test different prompt variations, such as adding dataset-specific context, few-shot examples, and COT explanations, to enhance feature selection performance. These changes aim to provide better context and improve the reasoning abilities of the LLMs during feature selection. Section Summary. In this section, we introduce three different approaches for feature selection using language models, LLMs. The first method, LLM score, involves selecting features based on numerical importance scores that indicate the relevance of input concepts to the target concept. The second method, LLM rank, ranks input concepts based on their relevance to the target concept. Lastly, LLM-SEQ employs a sequential selection strategy where concepts are iteratively added to maximize cross-validation performance. These methods are evaluated on real-world prediction tasks using various LLM models with different parameter sizes. Section: Decoding. In this section, we use greedy decoding as our default decoding method, which involves sampling with temperature T equals 0 for simplicity and determinism. However, since there is no clear ground truth for assigning feature importance and multiple reasoning paths can be taken, we also explore self-consistency decoding. In this approach, we set T equals 0.5 and average across 5 samples. We evaluate the performance of LLM score, LLM rank, and LLM-SEQ on small-scale datasets with around 10 to 70 features in various domains like healthcare and criminal justice. We aim to stress test these LLM-based feature selection methods in a small-scale setting and compare them with methods that are not as scalable to high-dimensional settings. We use both binary classification and regression datasets, including some published after the pre-training data cutoff dates to address concerns about data leakage. We measure the performance of each feature selection method by varying the proportion of features selected from 10% to 100% and observing how it affects the test performance of a downstream prediction model. We compare the LLM-based feature selection methods with several baselines such as LASSO, forward and backward sequential selection, recursive feature elimination, minimum redundancy, maximum relevance selection, filtering by mutual information, and random feature selection. We conduct experiments with different regularization strengths and feature selection strategies to decouple their effects on test performance. Overall, the LLM-based feature selection methods show strong performance comparable to the data-driven baselines when the LLM scale is sufficient. In Figure 2, we present the downstream test performance for classification and regression datasets when selecting the top 30% of features based on each baseline and LLM score using different LLM models. We observe that selecting features according to LLM-generated importance scores leads to competitive downstream performance compared to the data-driven baselines, especially with larger LLM models like GPT-4 and GPT-3.5. Similar results are seen for LLM-Rank and LLM-SEQ. For instance, on datasets like YouTube and NBA*, LLM score based on GPT-4 outperforms other baselines, demonstrating the effectiveness of using LLMs for feature selection. However, smaller LLMs may show less consistent performance, indicating the need for sufficiently large models for reliable results. Section Summary. In this section, we utilize greedy decoding as the default method for feature importance assignment due to its simplicity and determinism. Additionally, we explore self-consistency decoding with a temperature setting of 0.5 to address the challenge of multiple reasoning paths for determining importance. We evaluate LLM-based feature selection methods on small-scale datasets from various domains, comparing them against traditional feature selection methods and showcasing competitive performance with data-driven baselines when using sufficiently large LLMs. Section. Result 2. All three LLM-based feature selection methods achieve similarly strong performance. Figure 3. In this section, we present the results of our study. We found that all three feature selection methods based on LLM perform similarly well. When using GPT-4, these methods show strong performance, as depicted in Figure 3. The feature selection paths for LLM score, LLM rank, and LLM-SEQ overlap significantly on most datasets, except for diabetes progression and NYC rideshare. This indicates that even a simple strategy like querying for feature importance one at a time can be as effective as more complex methods. When we look at GPT 3.5 in Figure 3, we see a similar trend, although it is not as pronounced. Additionally, in the appendix, we observe that for smaller Llama 2 models, the performance of the feature selection methods varies more across datasets. This suggests that as the model size decreases, the effectiveness of each method becomes more inconsistent across different datasets. Furthermore, our study shows that zero-shot prompting without dataset-specific context and greedy decoding leads to strong performance, as shown in Figure 4. We evaluated different prompt designs and decoding strategies and found that the effectiveness of each method varies across different LLM models. However, we discovered that GPT-4 is less sensitive to the prompting strategy and generally benefits from additional context to some extent. This implies that zero-shot prompting combined with greedy decoding can be a strong baseline strategy for LLM-based feature selection. Moreover, we found that as the model scale increases, LLM score exhibits higher correlation with standard feature importance metrics, as illustrated in Figure 5. We measured the alignment between LLM score and various feature importance metrics and observed that the correlation generally improves with larger model scales. This suggests that exploring prompting strategies to enhance the alignment of LLM score with desired notions of importance could be a promising research direction. Additionally, we evaluated the performance of LLM-based feature selection on large-scale, high-dimensional datasets with around 3,000 features each. We focused on GPT-4-based LLM score due to its consistent performance on small-scale datasets and implementation efficiency. We conducted experiments on datasets extracted from the American Community Survey and the Mimic-IV database, evaluating the performance of different feature selection methods using various downstream prediction models. Overall, our study highlights the effectiveness of LLM-based feature selection methods across different datasets and model scales, providing insights into their performance and potential for improvement. Section Summary. In this section, we observe that all three LLM-based feature selection methods, namely LLM Score, LLM Rank, and LLM-SEQ, demonstrate strong performance across various datasets, with GPT-4 consistently achieving robust feature selection regardless of the selection mechanism used. Additionally, zero-shot prompting without dataset-specific context and greedy decoding prove to be effective strategies for LLM-based feature selection, especially with larger models like GPT-4. Moreover, as the model scale increases, LLM score shows higher correlation with standard feature importance metrics, suggesting potential for exploring prompting strategies to enhance alignment with desired notions of importance. Section: Baselines. In this section, we compared our LLM score based on GPT-4 with various feature selection methods. We used baselines such as LASSO-Net, Group LASSO, MRMR, Random Feature Selection, and an all-features baseline. Except for MRMR, we configured each method to select features at the concept level to align with the behavior of LLM score. For LASSO-Net and Group LASSO, we adjusted the settings to choose a similar number of features as LLM score. MRMR was set to select the exact number of features as LLM score. Additional details can be found in the appendix. The results showed that our GPT-4-based LLM score performed the best overall, outperforming LASSO-Net and Random Feature Selection on the Mimic-IV datasets. When selecting the top 30% of features, the test performance reached a plateau, similar to using all features. The feature selection paths for MRMR, LLM score, and Random Feature Selection were visualized for various datasets, indicating that only a small subset of features were highly predictive of the target outcome. LLM score effectively identified these crucial features, performing comparably to the best-performing baseline and significantly better than random selection when choosing the top 10% and 30% of features. The impressive performance on the manually extracted Mimic-IV datasets suggests that LLM score can excel even in complex domains like healthcare, where extensive domain knowledge is typically necessary for feature selection. Detailed results for all datasets and prediction models can be found in the appendix.